Hi, good morning. My name is Shinji Sato from Kochi University of Technology, Japan. My talk will be the tsunami risk assessment of Niigata City, accounting for soil liquefaction and snow melt. My co-authors are Takahito Ando and Yusuke Yamanaka from the University of Tokyo. As most of you may know, Japan has experienced the devastating tsunami damage by 2011 Tohoku Tsunami. Last year, I moved from Tokyo to Kochi, and now I'm living in Kochi, which is vulnerable to the earthquake tsunami of the Nankai Trough. But this time, I like to focus the tsunami risk of Niigata City facing the Japan Sea. As you see from this picture, we do not have the subduction zone on the Japan Sea side. However, occasional tsunamis are developed, as you see in this list in pink fonts, like 1964 Niigata Tsunami and 1993 Okushiri Tsunami. Based on the investigation of 2011 Tohoku Tsunami, Japanese government introduced a new strategy for tsunami disaster risk reduction based on level 1 and level 2 tsunami. I have talked this on the yesterday keynote, and this study focuses on the risk assessment of Niigata City by mega tsunami, so that this study focuses on the impact of level 2 tsunami. After 2011 Tohoku tsunami, government investigated tsunami sources in Japan Sea based on historical record as well as the geological data. About 100 sources are listed on the map with fault parameters and the slip length and the variance. We conducted tsunami simulation for these sources and extracted 3 sources, F34, 35, and 38, which is influential to Niigata City. Actually, F34 is the source of the historical Niigata earthquake tsunami in 1964. This is a picture of Niigata City. Downtown is located around here. Niigata is a historical port town formed on the fluvial sediment from 2 rivers. One is Shinano River, the other one is Agano River. The city is supported by many infrastructures like harbor breakwater, coastal structures, and the water gates. As you guess from this picture, the elevation of the city is very low because the city is developed on the river delta. Also, since the city is developed on the fresh fluvial sediments, it's fragile and vulnerable to the liquefaction during earthquake shaking. This map indicates that these areas have high risk of the soil liquefaction. A historical earthquake and tsunami was developed on June 16th in 1964. Many buildings were turned over owing to the soil liquefaction. Many infrastructures were collapsed by strong shaking, and later on, tsunami invaded through the river and to that community. There is a video showing some ideas of soil liquefaction and evacuation from tsunami. The ground appeared to be inundated only by soil liquefaction before the tsunami arrival. And later on, as I explained, tsunami attacked the city through the river. Niigata City is also known as a heavy snowfall. Therefore, we have significant river flood due to snow melt. Fortunately, the last Niigata earthquake was developed in June. However, we have to consider the next tsunami may occur in the snow melt season when the river water level is high. We conducted tsunami simulation of Niigata City due to mega tsunami generated by 3 sources. Sensitivity on infrastructure fragility and snow melt is investigated. The effect of soil liquefaction is also investigated in the evacuation simulation. Since we focus our attention to mega tsunami, the magnitude of the earthquake was assumed to be 8.1, and the slip length of the fault is assumed to be average plus 3 sigma, described in the table produced by the government. Okay, this is animation videos of mega tsunami simulation for 3 sources, F34, 35, and 38. The water level at the river mouth, Shinano River, is also shown on the bottom here. If we look at the tsunami height, the largest tsunami is produced by F34. And the earliest tsunami arrival is observed for F38. We calculated the flood area due to these 3 tsunamis and also the population in the flood area. As you see from this picture, the largest impact is produced by the F34, since it is the largest tsunami. And if you look at the effect of snowmelt, the effect of snowmelt appears to be small. However, if we consider the collapse of infrastructures, the damage will become more significant. So it is considered that the fragility of infrastructure is more essential to tsunami flooding than the snow melt. We constructed an evacuation model by using the result of tsunami simulation. We assumed that people start evacuation by walking from their home 4 minutes after the shaking. And the walking speed is this much. And the effect of the liquefaction is considered by the slowdown of the walking speed depending on the liquefaction degree predicted by the liquefaction map. The left picture shows a distribution of unsuccessful evacuation in the community close to the river mouth. You see a number of the people are assumed to be unsuccessful evacuation. This picture shows the percentage of successful evacuation for 3 sources with the scenario of collapse of structures. Horizontal axis denotes the start time of evacuation. It is confirmed that the effect of snow melt is once again minor. And the tsunami source F38 produces the largest unsuccessful evacuations, probably due to the early arrival of tsunami for F38. And also, if we consider the evacuation delay by soil liquefaction for F38, the percentage of successful evacuation is decreased significantly. To wrap up my talk, we identified 3 sources, F34, 38, 5, and 38, to be critical for the flooding of Niigata City, and the largest tsunami by F34 and the earliest tsunami by F38. And collapse of infrastructures are more essential than the snow melt flood. And successful evacuations were decreased significantly by soil liquefaction. Thank you very much for your attention.